Our next speaker is John Adams. As I mentioned earlier, John was the first individual to speak at an ICLR research seminar now almost 15 years ago. And John was the first person to speak more than once at an ICLR research seminar. So John is somebody who we've been working closely with over an extended period of time. John is with the Geological Survey of Canada, part of Natural Resources Canada, and part of the federal government, and one of the leading seismic researchers in Canada. He's going to share with us some of his perspectives on seismic hazard maps, in particular those associated with the Canadian Building Code and the process of sharing that hazard information with the building community and with Canadians at large. John Adams.
Thank you, Paul. I think one of the things that comes out of Dennis's presentation is that it takes a wide range of different disciplines to make this work happen. I'm coming from a geological background, and I'm going to talk more about the earthquakes and the geological reasons for them. I'll try not to be too technical. There aren't that many equations, but I think it'll give you some background as to what the cause of the shaking that is causing the problem with our society is. So a little bit of seismology background. An earthquake, a movement on a fault plane causes the vibration. And the larger the fault area, the larger the magnitude of the earthquake. Now, some of these earthquakes are very large indeed. For example, the large block of blocks there represents approximately the size of the Japan earthquake of March last year. The little square in the top left is the size of the Haiti earthquake 2 years ago, which really was the beginning of these earthquakes. And down here, in this little dot here, is about a magnitude 6.2 earthquake for comparison. And that's the sort of earthquake that we need to be most worried about for many of the Canadian cities. It's not the very biggest earthquakes necessarily. It can be the ones which are close but not quite so large. This shows that, in fact, you know, earthquakes are measured on a magnitude scale which is logarithmic, and we talk rather glibly about magnitude 6s and 7s, but you need to keep in context that the big earthquakes are really very big indeed. So magnitude depends on the size of the reactivated fault surface, and as the magnitude increases, the ground shaking increases by a factor of 10 for every magnitude unit. That's the logarithmic, so that's the side to side. However, the energy release goes up even faster. It goes up about 32-fold. So that as you go from one magnitude, say a magnitude 5 to a magnitude 6, the side-to-side shaking is going up by a factor of 10. As you go to a magnitude 7, your energy has gone up from 5 to 6, a factor of 30, and then 6 to 7, a factor of 30. That's 1,000-fold bigger. So these large earthquakes are very large indeed. In addition, the duration of the shaking increases, so that instead of taking a building and doing this to it just for a short period of time, you now start doing this to it for a very long period of time. And as Dennis showed, it's that reverse cyclic loading which causes the failure. You can think of it a bit like a coat hanger, a piece of wire. The more you bend it, right, the closer it comes to being brittle and failing. So that's another reason that the very biggest earthquakes are damaging. Now, major earthquakes are related to movements on the plate boundary. And we know where these plate boundaries are, and we can see the earthquakes on them. Canada has one little part of the British Columbia coast, which is a plate boundary. If we look at the distribution of moderate-sized earthquakes, magnitude 6 earthquakes for 20 years, they outline those plate boundaries very well. If we look at the bigger earthquakes, these are the 7.7s, nearly all of them are along those plate boundaries. And you'll see that if we look at eastern Canada, that in fact there are very few earthquakes away from plate boundaries during this particular time window. So that gives us a relative level for eastern Canada, very few earthquakes; for western Canada and the Pacific Rim, many earthquakes. We see that as we build up the map of earthquakes in Canada. So this is a history that goes back up to 350 years in Quebec, but maybe only about 100 years or more in the Canadian Arctic. And we see this pattern of activity, lots of earthquakes in the west, quite a lot of earthquakes in the southeast of Canada, or what we would consider southern Canada, and then a pattern in the north of Canada too. If we concentrate on the west coast part of this, and this is the area that's most significant for southwestern BC, effectively most of the population in British Columbia, we find that we have a plate boundary offshore, which is a spreading ridge. That's the red line going up there. And that generates small earthquakes, but they're also offshore, so they're not very damaging. However, underneath British Columbia, in the continental crust, that's the top 35 kilometers or so, we have large shallow earthquakes, which historically have been as large as magnitude 7.3 and could well be larger. Beneath those, we have a subduction zone. And this is a subduction zone exactly the same as the one that ruptured under Japan March of last year. It represents a place where the Earth's crust is diving underneath Canada, and it gets stuck there for a while and then releases its energy in a very short period of time. Effectively, that big earthquake, the one in Japan, was building up for a period of 500 or maybe 1,000 years and then happened very suddenly, within a matter of minutes. If we contrast and look at southeastern Canada, we have a distributed pattern of earthquakes around the area. I apologize, this was a presentation done mostly for Montreal, so this places Montreal at the center of the world. But a lot of the seismicity is in fact in that area of Western Quebec and in this region here, Charlevoix. In 1663, which is basically the beginning of recorded history, and even the records are not very good, we had an earthquake that approached to magnitude 7 in the Charlevoix area. And even today, we're seeing continuing activity of that. The last big one in Charlevoix was at magnitude 6.2 in 1925. But we've had other earthquakes in the Saguenay, which is the one that Dennis showed with the damage to the Montreal East Town Hall. That was a magnitude 5.9 in 1988. And that's the last really damaging earthquake we had in eastern Canada. If we come down towards the Toronto area, you'll see that the number of dots on there, which is a measure of the relative seismicity, decreases. But there are earthquakes a little bit further away from Toronto that have caused relatively strong shaking. Cornwall in 1944, Temiskaming in 1935, and Attica in 1929. Attica was on the New York side of the lake. So I've talked about the size of earthquakes being described by magnitude, and an earthquake only has one magnitude, but the effects are measured in terms of shaking intensity. And the scale that's most often used is the modified Mercalli scale. And you can think of this bullseye pattern here as showing you where the earthquake was felt and at the same level. The orange level is an area of quite strong shaking, the yellow less strong, the green and the blue. So effectively the energy spreads out like the ripples on a pond, and it gets smaller as it goes away. So that tells us that it's not only important the magnitude of the earthquake, but it also depends how close you are to it. We see here the magnitude 5.9 earthquake and the damage in Montreal, which is quite some distance away from it. I talked a little bit about the Cornwall earthquake in 1944. It's a relatively close earthquake to Ontario because it was actually on the Ontario-New York border. Magnitude 5.7, kind of threshold of major damage. In terms of today's losses, the damage was probably in the low tens of millions of dollars in current dollars. It was not a particularly damaging event. But we had a couple of examples where this is a brick house where the outside layer of the brick had failed. And one could imagine if this earthquake had gone on for a little bit longer, we would have probably seen a collapse in that building. The other thing that happened was that the bottom left here, you can see the parapet of the high school actually fell into the gymnasium. That's a known weakness of unreinforced masonry buildings, and I guess we're just very lucky that school wasn't in session at the time. Now, the most recent sizable earthquake was one near Val-de-Bois, a year and a half ago, June 2010. It happened in this region of Western Quebec, which we know is quite active. It was the strongest shaking in Ottawa's history. That's about 1 in 150 years, and it happened to be about a 150-year history. But if you look at the diagram at the top here, there's a little mountain of shaking in the bottom there, which was the shaking of that earthquake on rock in Ottawa. And the other two lines higher up are actually the design levels for buildings. So this Val de Bois earthquake in Ottawa only got to about 1/5 the strength that you would need for modern building design. So it was not that strong. It was felt over a very large area. You see the diagram at the bottom there. The star is in the center. It was only weakly felt into eastern Quebec, but into the United States it was felt down towards Kentucky. And you can see a number of greeny yellow dots around Toronto. Potentially an earthquake like this was felt by millions of people, potentially about 20 million people for this earthquake. And we get web reports from people. You can go onto the website and say, I felt this earthquake and this is how I felt it. So we had something like 59,000 reports of this. So we have a good idea of how it was felt. The effects in Ottawa at less than 70 kilometers, I happened to be out of town, which was kind of unfortunate. I missed the earthquake. And members of my family, 3 out of the 5 felt it. And I think as part of the population, unless you were running along or in a car or something, you felt this earthquake. So buildings were evacuated. The one in the middle is the Chefs on Parliament Hill. This was a late lunchtime earthquake, and so the parliamentarians may well not have got their food that day. You can see a chimney damage in Ottawa, which is typical. Chimneys are very tall, rather brittle structures. They're not that well engineered, and often the mortar's deteriorated, so you see that sort of damage. The top right is actually a chimney that fell onto a roof and then destroyed the entry to the church in Gracefield. And we also had some failures. This was described as a bridge failure, the one on the bottom left, but in fact it was the embankment leading up to the bridge that slid away into the lake. So all in all, this was a very big meteor event with a little bit of damage in Ottawa, but not very much. However, 400 kilometers away, it was a much more major event, and it was actually owned by Toronto. I have to say this company is really on the ball. 2 days after the earthquake, you could go online and buy these T-shirts. So the question is, how often do earthquakes happen? And this is a measure of magnitude recurrence statistics for those earthquakes near Toronto. The box at the bottom, which might be invisible at the back of the room, shows you the earthquakes that we know about, the history of them, and we've basically drawn a little box around them and say, we think we've got a bit of a seismic zone here. It covers the Niagara Peninsula, the western end of Lake Ontario, and upstate New York. From that box and the history of earthquakes, we can construct one of these magnitude recurrence relations. We find empirically that the numbers of earthquakes drop off. We have, it crudely goes like this. For every 100 magnitude 3 earthquakes, we have 10 magnitude 4 earthquakes and 1 magnitude 5. So it drops off by a factor of 10 roughly for each magnitude. And that's shown here. The cumulative rate, this is the 1 per year event, is about a magnitude 3 earthquake in that area, somewhere in that area. It wouldn't necessarily be close to Toronto. And we can take that rule and extrapolate it to the magnitude 6 earthquakes. These are the ones which we get interested about because they have the potential for damage. And in that larger area, the expected rate is about 1 every 3,000 years. Now, I have to say, saying it like that makes it uneasy for us to understand, but the right way of thinking about it is the annual probability of 0.0003. Yeah, 0.0003. So the annual probability, this earthquake could happen next year, but with quite a low probability, and every year thereafter. It's convenient to turn around and say, well, once every 3,000 years on average, we'll have an earthquake like that. The black arrow here gives you an idea of the uncertainty, and it's pretty damn large, because this is about 1 in 500 years, and this is almost never, right? We have a real problem that the events that are most important in terms of damage and losses and impact on society don't happen very often. And so we have to take the statistics that we do have and extrapolate them to low probabilities. We should sort of answer the question, why do earthquakes happen here? Because if we have a good model underlying the origins of earthquakes, we can perhaps use it to make better extrapolations. This map shows the seismicity across southeastern Canada. We have some areas which have relatively active clusters of activity, but there are also areas that are not quite so active. The one at the bottom here is Montreal, Charlevoix, which had that magnitude 7 in 1663, an area in the lower St. Lawrence, and the one right on the left there is the upper Ottawa Valley Temiskaming. And between the two leftmost ones, that's the West Quebec zone where the Val de Bois earthquake happened. Now, we do have some geological understanding of what happened. There was an ancient rifted margin that went up the St. Lawrence and then goes down towards New York. That used to be where the Atlantic Ocean was before the current one. Some 500 million years, an Atlantic, a proto-Atlantic Ocean opened up, and all of this land here, basically the Appalachian Mountains, was actually on the far side of that proto-Atlantic, and it was effectively part of Africa. 400 million years ago, it came in and pushed up against it, but the faults that caused that rifting in the first place are still there. You can see them in the landscape. Geologists can map them. And we know that they roughly extend down that region. There are also a couple of failed rifts. These are the oceans that did not open. They failed to open in the Saguenay and the Ottawa rivers. Now, the argument we would say is that these are areas where the crust, which was quite strong, has been broken. And once it's broken, it's relatively weak, and that's the place where the earthquakes will happen today. One of the youngest things that happened, and I'm a geologist, so young is 100 million years ago, right, long time ago, was that North America went over a hot spot, a bit like the one that created the Hawaiian Islands. And as it moved over this hot spot, the heat basically heated up the crust, bowed it up, and cracked it. And it also caused volcanoes at Montreal and across the eastern townships. So that's a feature that reactivated old faults about 100 million years ago. We believe today that all of these earthquakes represent compression of the whole of North America, if you like, between California on one hand and the middle of the Atlantic Ocean. And we're squeezing it like this, and these faults, which were relatively young, right, relatively weak, are the places that the earthquakes have happened and will continue to happen. Now, you'll see that none of these very big lines goes through Toronto or in the Toronto area. And those ones, we think that there are even older faults which perhaps haven't been reactivated very much, which are still weak enough to cause small earthquakes. But we think most of the action will be on those thick lines. Now, we can't stop the earthquakes happening. The idea of, if you like, nailing one side of the plate to the other won't happen. We can't forecast them yet in a very useful way, and so really we have to mitigate their effects. Globally, most deaths in earthquakes are from people killed in collapsing buildings, something like 2/3 of them. Now, I have to say that that's a global estimate, and we don't have the same problem of collapsing buildings that happens perhaps in Turkey and Pakistan and other countries. You'll see that the purpley color there, tsunamis are a relatively large cause, and we're certainly going to have tsunamis on the west coast of Canada, but fortunately we don't have anything like the population exposed to it that Japan did. And then there are other causes as a consequence of those earthquakes. Now, in Canada, we have done something about the collapsing building through the building code. And the National Building Code is the minimum standard to protect the life and safety of building occupants and the general public as the building responds to strong shaking. Now, I have to say, it doesn't protect you from very large economic losses. A success in this field is often that you can walk out of the building, but the building has to be torn down. There is a different category, which is the continued operation, the one Dennis was talking about, where after an earthquake like this, we really want our hospitals to be operational, so they have to be built to a higher standard. Now, the expected shaking comes from seismic hazard maps, and these have been done since the 1950s by the Geological Survey of Canada as the contribution to the National Building Code. Here's roughly how we do it at the moment. A probabilistic seismic hazard map. We start with an earthquake catalog, which we've built up over 300 years. Still a very small snapshot. We have the magnitude recurrence statistics, like that graph I showed you for Toronto, that says that the chance of a big earthquake is less likely than a small earthquake. We need a ground motion prediction equation that says that if the earthquake happens here with this size, then the ground motion has died away with distance at a certain rate. And that's an expertise that Gail Atkinson has and we'll talk about next. And then finally, we do an integration of this to come up with a seismic hazard map. Now, the first map was done in 1953, and you might ask the really valid question, I'm living in a building that was built in 1940, is it earthquake resistant? Well, a lot of buildings have a fundamental earthquake resistance to them, but it wasn't engineered in. So if it was there, it was because of general robust construction. But the state of the art has moved forward so far that the buildings that we construct today are far, far better than they were back in the 50s and 60s and 70s. The 1953 map was basically one map, and it was primarily a zoning map. It had actually just divided Canada up into 4 zones in a rather qualitative fashion. The 1970 map was a probabilistic map at 1 in 100 years. That's a relatively common probability, and it gave the peak acceleration for 4 zones across Canada. In 1985, the one map was replaced by 2 maps. We now have maps of peak acceleration and peak velocity. The reason for that is that peak acceleration is a very high frequency motion, and it's most relevant to the design of short buildings like 2 to 4 story buildings. If you're starting to design 20-story buildings, peak acceleration is really not a very good input. It divided Canada up into 7 zones. It took into account a rock and firm ground category, that was basically good, and then various soil categories. And it was probabilistic at 1 in 475 years. So you can see we were actually pushing that probability level down. The 2005 maps, which was really my first contribution to this, we now have 4 maps. We've gone from peak acceleration and peak velocity to spectral acceleration, which better describes the shaking as a function of period. There are no zones in these maps any longer. We used to divide Canada up into 7 zones, and the problem was this, that if you were on a zone boundary, the design level jumped by about a factor of 40% across that boundary. Now we effectively have contours across the whole country, and you don't get those step discontinuities. The definition is now firm ground, but you're allowed actually to reduce the acceleration on rock, which is appropriate and correct. And these maps are probabilistic at 1 in 2,500 years. 2% in 50 years. The argument there is that a building that we construct today has a lifespan of about 50 years. The 2% is we want 2 chances in 100 that it will have to go through its design shaking during its life. One might look at this and then say, well, I'm going to build a national museum that I think should be there for 500 years, right? And then you might decide that you actually want to design for a longer period or a lower probability. The 2010 maps are effectively very similar to 2005, but with a few tweaks, which I'll show. Now, the National Building Code for 2010 was issued at the end of 2010, and it's in the process of being adopted by the provinces and territories. And I must admit, I don't know whether today Ontario has adopted it. It becomes part of the Ontario Building Code. And then when you see the building which is being started across the street, it's built according to a building code that was in effect as part of law in the province at the day in which the plans were approved. The chief difference between the 2010-2005 models was the way in which we did the ground motion predictions. We changed from a quadratic to an 8-parameter fit. So crudely, we had a 3-parameter fit before. We've got an 8-parameter one now. And this reduced some unnecessary conservatism. In particular, it reduced the hazard at short periods in low hazard regions, and it increased the hazard a little bit at the long period end. And these were almost just tweaks to the model, but they did take out design levels which were too conservative before. In particular, I talked in the beginning about peak ground acceleration. Peak ground acceleration is not used for building design under the building code at the moment, but it is still used for geotechnical design. And this graph here shows the way the changes, it changed a little bit. These are spectra which show the level of shaking in the vertical against the period, and these tilt a little bit according to whether you go from 2005 and 2010. I would say that those differences don't look very large on here, but I'm a scientist, and in order to show this, I've put this on a log-log plot. And you can imagine if you put this on an arithmetic plot that the differences are much larger. Now, Natural Resources Canada website has a seismic hazard calculator for doing this. You can go to our website, earthquakescanada.ca, which is at the bottom. You can go to earthquake hazards, and you come up with a page that says Get 2010 Hazard Values. You type in the coordinates of your site, and you get a seismic hazard calculation for that particular national building code. A little bit further down, it also gives you the probability of shaking for other probability levels, more common probabilities, unfortunately not lower probabilities. So the 1 in 100-year shaking is there as well. Since this audience might be doing a lot of this, this is kind of a one-off. If I'm an engineer and I'm designing a building, I type in the coordinates, there's the value. But we have also published the entire data set, which is 250,000 points for the whole of Canada. So you could actually just basically download that report, and that effectively gives you a detailed map. Now, I wanted to spend the rest of the talk looking forward to where we're going for the next National Building Code in 2015. And at the moment, our trial results are on computing and understanding the hazard values for the populated parts of southeastern and southwestern Canada. Now, the reason that we do this is that our assumptions and input and data and understanding have changed since we last did this. And they've changed quite a lot, and so we can expect the hazard values to change too. What we're doing is effectively making our best estimate of the true value according to the information we have at hand. We don't know the true value, we're just estimating it, and that's why the numbers change as we get better at doing this. For example, we've had quite a lot of new earthquakes. The last model that we had, the one used for 2005 and 2010, used earthquakes up to the beginning of the 1990s. So we've got something like 20 years more earthquakes. This adds a lot of small earthquakes to the data set, which actually aren't that interesting or important, because we now locate about 4,500 earthquakes every year in Canada. But we do add a number of significant earthquakes. For example, over the last decade, we've added the Denali earthquake in Alaska, which was very close, the Nisqually earthquake under Puget Sound, which was a very interesting one because it was the first strong one that we had in that region. We've added an earthquake in the Queen Charlotte, earthquakes like the Val de Bois, etc. So we are adding a lot more data to the understanding. We've improved our catalog magnitudes. I talked a little glibly about the magnitude of an earthquake, but unfortunately there are about 5 different versions of it. It's a little bit like saying, I've got a 1-inch nail here and it's also 25 millimeters long. They all try to do the same thing, but they never do it precisely the same. So we've now standardized on a moment magnitude catalog, which means that at least all of the magnitudes are now equivalent in each place across Canada. We're also trying to explain a little better how these earthquakes relate, and therefore how the extrapolation to get the seismic hazard is coming along. I talked about the St. Lawrence Rift. This is the one that was formed by the Proto-Atlantic Ocean, and we see seismicity along it, which is in clusters, but we also see seismicity in between it. So we think that those parts of the rift are equivalently active, perhaps. May not be that active in the short term, but in the long term, we think that they probably also will have large earthquakes. We tackled this in the 2005-2010 approach by having 2 models, one which had earthquakes in clusters and the other which had spread the earthquakes out over a larger region. And these had rather different implications for the seismic hazard. What we did as an engineering conservatism is took the worst of those 2 cases and used that for engineering design. Now, that's not actually a probabilistic calculation, and if you're doing something like estimating your dollar losses from an earthquake, it's actually not a very good way to do it because you've actually double counted, you've actually increased the numbers a bit, right? So it's not quite so good. But from an engineering conservatism point of view, and remember this was built around the thing, we don't want buildings to fall down. It was a reasonable thing to do. But we would really like to change that, and we're hoping to go to a fully probabilistic model in 2015. We're drawing boxes around the earthquakes that we know about. We can calculate the magnitude recurrence statistics. And different places along here have different levels of activity. The one at the top, the high level of activity, is the place which has the most earthquakes, and then there are areas which have low levels of activity. But we worry that this doesn't capture the potential for the next big earthquake, which may happen in a place somewhere else. To do that, we've actually redefined very large zones. Instead of having those little earthquake clusters, we've grouped the regions along those seismotectonic structures into single sources. So we have a source that goes all the way down the St. Lawrence, and we use that, we basically populate that with rare big earthquakes, which we think will happen maybe once every 300,000 or 3,000 years. So the model that we're intending to use has the seismicity in the clusters. That says that what happened last year and what happened in the last 100 years probably will happen in the future. But we're going to add on to it these large, rare, big earthquakes, which we've taken somewhat arbitrarily to be those larger than 6.8. And we think those could happen over a much larger area, including, for example, the southern Great Lakes, Lake Erie, Lake Ontario, and the area around them. And so the model comes down to this. The rates of these earthquakes are relatively low. Even along the St. Lawrence, which is the highest, it's still about 1 in 300 years. And it's 1 in 300 years along a very long ribbon, which means that the chance of it happening very close to any particular place is relatively small. If we get down to the Toronto area, the southern Great Lakes, we're into about 1 in 3,000 years for these rare big earthquakes. And you'll see that that's actually higher than the expectation from that source zone around the western end of Lake Ontario. So we think that these big rare earthquakes are actually a little more common than the historical expectation would give you. They do contribute quite a lot to the seismic hazard. In Montreal, about half of those highest bars actually come from those rare big earthquakes. That's because the seismicity in Montreal is quite high already. But if we go to Trois-Rivières, which is a relatively low seismicity region between Montreal and Quebec City, you'll see that the contribution from these rare big earthquakes is much larger. And that's largely because there haven't been very many earthquakes close to Trois-Rivières in the recent past. Remember, we're taking a maybe 300-year earthquake history for Trois-Rivières and asking the question, what's the 1 in 2,000 or 3,000-year earthquake like? And so that extrapolation, we can't do it just based on a very short history. We also have to have geological and other inputs. I'm going to move briefly to the western part of Canada. We know that this is near a plate boundary. Things are more active. We've got sources there which are drawn in a somewhat similar fashion. We do have to be a little bit careful, and last time we included some of these small clusters of earthquakes. This map here with the red arrows is the Alberta foothills. And some of the oil and gas extraction there has actually caused earthquakes. And those clusters of earthquakes, we think, are not going to be of the nature that is going to give us damage to buildings. They won't be large enough. They may be smaller and often. And one would get the wrong expression. If you had that very high level of seismicity and extrapolated, you end up getting a very low rate of magnitude 5 earthquakes, where we think the actual one is somewhat higher. Under Puget Sound and Vancouver Island, these purple areas are the subcrustal earthquakes that are happening. These are not the ones on the subduction interface. We'll come to those. They're actually ones in the downgoing plate as it bends. And the seismicity level is quite high in that region. So that needs to be taken into account. Last time, we had a deterministic model for the Cascadia earthquake. We basically assumed that this Cascadia earthquake happened. It had a magnitude of 8.2 and it caused shaking. We're now actually modeling it in more detail. And what matters, as it did in Japan, is where that subduction zone is and how close the closest part of it comes to the population centers. So we have a scientific description here of the inboard edge of the rupture. For comparison, Vancouver, Victoria are up in this region here. We modeled the subduction zone as a dipping, downgoing slab. And what we're interested in is how close the closest part of this slab is to Victoria and Vancouver. And the answer is it's about 60 kilometers horizontally away from Vancouver and 30 kilometers down. So you're about 65 kilometers away from it. Vancouver is nearly twice the distance. And that means quite a lot in terms of shaking, because the shaking dies away relatively rapidly with distance. Relative to the way we did it for the last building code, this locus is about 15 kilometers closer to Victoria. In other words, we've decided that now we think the shaking will be a little closer to Victoria than it was. We have a paleohistory of great earthquakes on the subduction zone, probably one of the best earthquake histories in the world. There's some discussions about how good it is, but it's basically a 10,000-year history of these great earthquakes. And for the things we're concerned about, every one of these earthquakes was a bit like the one in Japan in March. But we do have 10,000 years of history. And we can take that 10,000 years history, and we can say that the prototypical event happens about every 550 years. It ruptures a length of about 1,000 kilometers from California to the middle of Vancouver Island. The width of the fault, which is the down dip, is 125 kilometers. So remember I showed you that picture of Japan, which had the little squares. So we've got a block which is 1,000 kilometers long, 125 kilometers wide. It slipped about 25 meters in each event. A lot of slip. The magnitude somewhere around 9.3. Okay, and there are different assumptions that can go into that. But the prototypical Great Cascadia event is this event. The last one that we had was in 1700 AD. We know that from geological evidence on the west coast of Canada. We know it from the tsunami that turned up in Japan about, 20 hours later. So we know these earthquakes have happened in the past. We know now, we actually have a 10,000-year history of them. We know they happen about every 550 years. The unfortunate thing, though, is it's not like the beating of a drum. It's not as if you can say, we're safe now for 250 years. You know, the last one was 300 years ago. Because they happen with short intervals, they happen with long intervals. So this earthquake is something that has a probability of happening next year. Not a very high probability, but it's a probability. Now, I've talked about magnitude, and you would think that it would be easy to say the magnitude of this event is, but in fact, we've got a couple of ranges there. We say it could, these prototypical events are around magnitude 9.3, but it could actually be smaller because some of the properties of the zone mean that the size could be a little smaller. But in fact, it doesn't make a lot of difference to the shaking levels of the cities nearby, because a lot of the fault is a long way away. The stuff in California won't cause damage in Vancouver. It's only the stuff nearby to you. We have this is a magnitude recurrence curve which shows the sort of the two ranges of magnitudes we're worried about. The largest one here, we would say the top estimate is somewhere around 9.5, which makes it about as big as the Alaska earthquake in 1965, a little bit bigger than the Japan earthquake. The prototypical one, the expected one, is actually probably a little bit smaller than the Japan earthquake that just happened. And we get a shaking map. This is just a crude to show you the shape of it. It really matters how close you are to this blue line, and you can see it dies away as you move inland. We're fortunate that relative to Japan, we have very little population on the outer coast of Vancouver Island. Japan was densely settled. We just don't have as many assets at risk. I'll just move back to the middle of the country. I've talked about southeastern Canada, I've talked about western Canada. Middle of the country, you'd say, but there are no earthquakes there. Well, there are some earthquakes. We see earthquakes in Saskatchewan relatively often, maybe a couple of times a year. We had a magnitude, I think it's 5.3 earthquake there in 1909. So we don't think any place in Canada is safe from earthquakes. We just think the probabilities are relatively low. This paper is a very good one talking about how big earthquakes can be in the middle of continents. And it comes from an Australian data set where the preservation of the evidence is really excellent. It's a very dry country. The faults tend to break the surface. You can see the fault scarps. And they have hundreds of thousands of years of fault scarps which they can look at. Their conclusion is earthquakes in the middle of continents could be as large as 7.2 or so. And so that means at some very low probability, there's a chance of an earthquake of that size in Manitoba or Saskatchewan. And so we did, in 2005, come in with a certain amount of seismic zoning for the middle of the country. Now, it happened that the level was not very high. It really didn't change engineering practice very much where it was adopted. And in fact, in Manitoba, they decided that they didn't want to bother with it. But there was, at least we were trying to say, there is a risk in the middle of the country. It's so much lower than in Toronto or Montreal or Vancouver, but it isn't zero. I'm coming towards the end. Gail Atkinson, who is following me, will talk about the new ground motion prediction equations. These are the things which changed the hazard estimates the most, because as we went from almost no data to some data to we're beginning to get quite a lot of data, and so our estimates are getting better on that basis. I talked about the evolution of spectral periods. These are things that are important for the way the buildings are designed. And the building design, we're now getting these spectral periods which are appropriate for the design of buildings of different heights, and those are really quite important. The other thing that's important is that we've got better adjustments for the reference ground conditions. In 1985, we just threw in rock and firm ground, and we said, well, you know, if it's a certain level of strength, a bearing capacity, you would build for it. But in 2005, we actually said that firm ground was the reference condition. That's because we think it happens most often in many places across Canada. And if you're actually on rock, you can reduce the ground motions by 20 to 50%. Now, most of the high-rise buildings, for example, in downtown Toronto, are built on rock. It's not really, really hard rock, but it's quite good rock. And so, in fact, though some of the factors that went into the building code increased the level of design, the fact that the buildings were on rock here, they actually reduced the levels of design. So that was a good thing. And as we move forward, the reference ground condition will be quite clearly specified. It's probably going to be this class B/C, the boundary between B and C. That's a US definition, and we'll probably just follow them because it's simpler to use it than not. I think Darius will talk about other factors on soil factors, because as you go from Class A to Class B, the ground motion goes up a little bit. As you go up to Class C, it goes up a little bit more. As you go up to Class D, it starts to get quite a lot larger, and if you're on Class E, it's much larger still. So you do have to take the soil amplification into account. Okay, to summarize, I'm probably a little behind time, but what I want to say is that our seismic hazard estimates are improving. I've shown you where you can get the latest estimates on the web, so if you're interested in a particular product, you can get the current design level. I've also talked a little bit about the improvements and the increased confidence that we're having, and we think that the 2015 estimates will provide an improved basis for the distribution of engineering design. And then they should be of use to the wider community because they effectively become our best estimates of the shaking to be expected in the future. Thank you.
Thank you, John. Any questions for John? Here first.
Just a personally question today for you. Has there, from all the analysis that you've done, has there ever been a tsunami on the Great Lakes or rolling up the St. Lawrence?
Sorry, can I briefly have you introduce yourself?
Introduce yourself. Tom Schultz from RSA.
Thank you, Tom.
Tom Schultz from RSA. The question was, has there ever been a tsunami on the Great Lakes? We've had things that look a bit like tsunami, which were probably meteorological SAIS events. Okay? I don't think there's never been one that people say, yeah, this was definitely a tsunami. To be a tsunami, you have to have quite a large earthquake. It takes about a magnitude 6 to 6.5 earthquake, which would have a rupture length of 10 or 20 kilometers, move one side up by a meter or so in order to generate a tsunami going like this of a couple of meters, which could get bigger as it came into shore. I've done some, this has been an issue for some of the design for nuclear power plants. People have been worried about this after Japan. We don't think that, well, we're certain that earthquakes as big as Japan can't happen here. There is a small chance that an earthquake big enough to cause a tsunami could happen. It's about a 1 in 10,000 year-ish event for the Southern Great Lakes. It's actually a pretty rare event. And the chances are it would be of the order of maybe 2 meters or so. It's not a particularly large event. The probability isn't 0, but it's pretty close. I think there are a lot of other things to worry more about.
When you ask your question, if you could please use the microphone and keep the question short, because we're short on time. Thank you.
Otto Pilt from Emergency Management Ontario. Just like to ask about the recent earthquake events in Ohio and Oklahoma, which apparently people now think were caused by hydrofracturing? And is there a risk of that kind of earthquake in Canada?
So we do know that some earthquakes are caused by human activity. The most obvious ones are if you fill a dam, sometimes you will induce earthquakes. And that's thought to be a combination of the weight of the water in the dam and the fact that the water pressure has increased. You've now got more head of water. We know that certain water well disposal activities can cause earthquakes. If you pump water down into a deep horizon, you can actually generate earthquakes. The water spreads out, increases the pore pressure, and effectively it causes an earthquake that was ready to happen. It brings it forward to the present. And so on the south shore of Lake Erie around Ashtabula, there's an area where disposal wells have caused earthquakes like that. They were up into the magnitude 4.5 range. The one that happened in, was it Ohio, Youngstown? Okay, that was a magnitude 4. It was in a downtown area. Didn't cause very much in the way of damage. It's been linked to a disposal well, okay? Now, I wouldn't say that the link is exactly like this. It's kind of a little more tenuous than that. But it seems possible that disposal well actually induced the earthquakes. There's been quite a lot of confusion in the public between water disposal like this and fracking, because in both cases you pump water down or fluids down a hole, but the fracking process is very different in a lot of ways. Very little water is used. You actually don't want to crack large amounts of rock because you want to contain the gas within the area you're trying to take out. And so it's going to be one of these things where there is a real need for public information on this field, because there's a lot of confusion between disposal wells, induced earthquakes, and fracking. So.
It's time for one more question. One more? Yep, Paul.
Paul Cutbush from Swiss Re. About 8 weeks ago, there was some research, I think it was University of Oregon. They'd been doing some research, I guess, between Vancouver Island and Washington, saying that they think that the dip slip, I guess, is deeper. They're saying that actually megathrust earthquakes could possibly have larger damages to places like Vancouver and Seattle. I saw one newsprint, it was released, and nothing else came out. I wonder if you could elaborate on that, please.
So I don't know exactly what they were basing it on, but we too, the work by my colleagues at the Pacific Geoscience Centre, part of the Government of Canada on Vancouver Island, came up with that location for that inboard edge. And we have moved it 15 kilometers closer. It may be they've done something similar. There is a process for doing this. There are US maps that happen on a similar sort of cycle, a little more commonly than Canada. And we go along to their workshops and they give us feedback to ours. And there's a workshop on that took place in December. There's another one coming up in February. And, March. And our experts go down and talk. And we try and make sure that we don't have very different opinions of what's going on. But the science seems to be relatively good. And if it changed, it may have changed in the same way we've changed it on our side of the border.
Okay, thank you, John.